This lecture concludes our series on the fundamental idea of the chemical composition of compounds. Now, in this video, we focus on one of the great identifiers we have in chemistry, the molecular formula. Now, this formula not only identifies all the atoms in the molecule, but when linked to the molar mass, allows us to measure rather precisely the number of molecules of the compound and the very number of atoms using a simple lab balance. Now, up to this point, we see that it's relatively straightforward to calculate the empirical formula from experimental elemental mass data. To get the molecular formula, we're going to need an additional piece of data, and that will be the experimental molar mass of the compound. Now, the data can be obtained with analytical measurements such as mass spectroscopy. Remember, the only difference between the empirical and molecular formula is a simple integer multiplier, n, for simple compounds, and it's this integer multiplier we want to compute. This multiplier, n, is simply the ratio of the experimental molar mass, which we assume represents the molar mass of the molecular formula, divided by the molar mass of the empirical formula. Now let's return to our hydrogen peroxide example from the last lecture. Let's say we found experimentally using our mass spectrometer that hydrogen peroxide has a molar mass of 34 grams per mole. From our previous lecture, we found that hydrogen peroxide has an empirical formula of HO. We first need to calculate the molar mass of this empirical formula. The value is 17.01 grams per mole. Now, to get the n multiplier, we divide the actual molar mass by the empirical value, giving us a final value of 2. From here, it's a simple matter to multiply each of the subscripts of the empirical formula by 2, obtaining the real molecular formula for hydrogen peroxide, H2O2. Now, for our reference, a simple structural formula for the hydrogen peroxide is HOOH, where the red atom is the oxygen atoms and the white is the hydrogen atoms. There are many interesting questions that we are now able to handle. Let's do a few of these. If we have 34.0 grams of the compound vanillin, which has a molecular formula of C8H8O3, how many moles and number of vanillin molecules do we have? Now, what we have is grams of vanillin to moles of vanillin in our solution map. The grams-mole link for compounds will be the molar mass of the compound. Now we find the molar mass for vanillin to be 152.16 grams per mole to 2 decimal places. The molar mass is the critical relationship we need to convert mass to moles. 1 mole of vanillin equals 152.16 grams of vanillin. Now, to work our problem, we divide 34.0 by 152.16, canceling the grams of vanillin, obtaining a final value of 0.223 moles of vanillin. Now, to get to the actual molecules of vanillin, we simply multiply the moles of vanillin by Avogadro's number. Using the molecule in the previous example, what would be the actual mass in grams of each of the elements in 34.0 grams of vanillin if we tore the molecule all the way down to the elemental level? Now we're going to be starting with 34.0 grams of vanillin, and we want to get to grams of each element. Now, this step leads to another Striplinism that I use when discussing chemical computations. Usually, grams suck. When doing chemistry, we do the chemistry in moles, not mass. What this saying means is that if we're going to do chemistry or anything else with a compound that requires calculated amounts, more than likely we'll need to turn all of the masses in the problem to moles first. These kinds of calculations are called stoichiometric computations. Now, in the previous problem, we changed 34.0 grams of vanillin to its equivalent 0.223 moles. We now will use the subscripts on the molecular formula to give us the correct mole ratios of the elements within the compound. In this case, we see that for every mole of vanillin, there will be 8 moles of carbon, 8 moles of hydrogen, and 3 moles of oxygen. That is the link we need, moles of vanillin to moles of elements. Now we need the link between the moles of elements and grams of elements to finish the problem. We're already familiar with this computation. The relative atomic mass on the periodic table gives us the link between the grams of an element to 1 mole of the element. Done. Now we do the computations. If we did it right, all the masses add up to 34.0 grams. Not too bad. Let's do one more problem. What would be the mass percent of each element in the compound with the molecular formula C4H12N2? Now, the percentage calculation described on this slide is a common one conducted by chemists when they synthesize a new compound. We estimate what the elemental percentages will be from the molecular formula of the compound we think we made. We then send a small amount of the compound to a respected analytical lab that measures the percent mass composition of the elements. Hopefully, the analytical percentages will match up with the percentages of the molecule we think we made, proving we have what we think we have. Now, to get the percentages from the molecular formula, we need not only the mass of each element, but also the mass of the total molecule as well. To do this problem, we assume we have 1 mole of the compound. We now know we can easily get to the total mass of the compound by simply multiplying 1 mole of the compound times the molar mass of the compound. Again, starting with 1 mole of the compound, we use the superscripts on the molecular formula to get the mole-to-mole ratio of each element. From here, we multiply by the relative atomic mass of each element to get the final mass of each element in 1 mole of the compound. Now we take the ratio of the mass of each element in 1 mole of compound by the total mass of 1 mole of the compound and multiply by 100 to get the final mass percentage value for each element. Many concepts came together in these last few lectures, and now we have most of the foundational computational tools and techniques we need to calculate amounts and quantities common in everyday occurrences in the chemical laboratory. Now, the kinds of computations we've done are analogous and just as fundamental to us as assuming that everyone knows how to add, subtract, multiply, and divide when graduating grade school. So, it goes without saying that these are very important computational skills and critical assumed knowledge for all chemists and chemistry students. Now, work hard to make these kinds of computations automatic. Catch you later.